Alright guys, we're talking about logic, and this is our second day. We will finish it up today. Now, I do want you to notice on the screen, this is a warm-up that we would traditionally do in class, but due to the flipped classroom, this is what I want you to do. Basically, if you have an index card or piece of notebook paper, what I would do is begin creating a kind of a graphic organizer of all of the different types of symbolic notations and logical statements. Okay, so this is what we have so far. The last of these that we will learn today is called the biconditional. Okay, notice that the arrow goes back and forth from P to Q and then Q back to P. We could say this is also P if and only if Q. Okay, so that's going to be our main topic a little later today. But we're going to do some examples of conditional, converse, inverse, and contrapositive first. Okay, so if you want to go ahead and pause and fill this out for your future reference. Alright, logic, day 2. Alright, so if we take a look here, I have a conditional statement that if it is raining, then the streets are wet. So the converse of that, remember, you're going to switch the hypothesis and the conclusion. So, if the streets are wet, then it is raining. The inverse, you keep the same conditional statement, if it is raining, then the streets are wet, but this time you negate the hypothesis and the conclusion. So if it is not raining, then the streets are not wet. The contrapositive, you switch both the hypothesis and the conclusion, and you negate both. So if the streets are not wet, then it is not raining. So taking a look here, we need to determine if it's true or false. We're going to be using counterexamples similar to what we did in inductive reasoning. So for the converse statement, if the streets are wet, then it is raining, I would say that this is actually going to be false. And the reason for this is what if there's sprinklers on, right? Could the road be wet for any other reasons besides rain? Yes, sprinklers, maybe a water pipe burst, all kinds of reasons, okay? Alright, now the inverse, if it is not raining, then the streets are not wet, I would also say that is false due to the same reasoning we used in converse. And contrapositive, if the streets are not wet, then it is not raining. So that is true. So we started out with a true conditional statement, and the only statement that was also true was the contrapositive. Alright, looking at conditional statement number 2. If 2 times x is 10, then x is 5. So again, we're starting out with a true conditional statement. The converse is, if x equals 5, then 2x equals 10. Well, that's true, right? Can't find a counterexample for that. Inverse, if 2x is not equal to 10, then x is not equal to 5. Well, that is also true. And the contrapositive, if x is not equal to 5, then 2x is not equal to 10. That is all true. So we started out with a true statement and ended up with all 4 being true. So it says answer some questions. Does the truth of the conditional statement automatically guarantee the truth of the converse? Well, looking at our first example, we can say no. We started out with a conditional statement that was true, and the converse was not true. Does the truth of the conditional statement guarantee the truth of the inverse? No, for the same reason. But if the truth of the conditional statement, it will guarantee the truth of the contrapositive. Alright, so let's do some more examples. Here's a conditional statement. Okay, I'm starting out with one that is false. Okay, I can plug in -2 for -2 squared equals 4. Okay, so the converse is, if x equals 2, then x squared equals 4. Well, that's a true statement. If x squared is not 4, then x is not 2. That's also true. And then the contrapositive, if x is not 2, then x squared is not equal to 4. And that's false for the same reason as the conditional statement, x equals -2. Alright, now, here's a conditional statement that's also false. 2 times x equals 10 if and then x equals 3. Well, that's false because x has to be 5. So looking at the converse, if x equals 3, then 2x equals 10. Well, that has to be false because 2 times 3 is actually 6. The same reasoning goes for inverse. And then taking a look at our contrapositive, if x is not 3, then 2x is not equal 10. Well, okay, let's pick an x. X is 5. It's not 3, but 2x is equals 10. Okay, so that is a false statement. So let's look at those two previous examples. Does the conditional statement being false guarantee that the converse will also be false? The answer to that is no. Does the conditional statement being false guarantee that the inverse will be false? No. And does the conditional statement being false guarantee that the contrapositive will be false? And the answer to that is yes. Notice that in both cases, the conditional statement and the contrapositive were both either true or false. And we call that logically equivalent. Okay, the conditional and the contrapositive are going to be logically equivalent all the time. If one is true, the other is true. If one is false, the other is false. Whatever they are, they must both be the same thing. Alright, so let's complete the table. The converse propositional form, if Q then P, is or is not logically equivalent to the conditional statement. Well, we know that is not true. The converse is not logically equivalent to the conditional. Is the inverse in the propositional form, if not P, then not Q, is it or is it not logically equivalent to the conditional statement? That is not. Part C, the contrapositive will be logically equivalent to the conditional, if P, then Q. That is the only one that is logically equivalent. Alright, so for A, if you know the truth value of the conditional statement, what can you immediately conclude without any more information about the truth value of the converse? We cannot make any conclusion. What can you conclude about the truth value of the inverse? No conclusion can be made. What can you conclude about the truth value of the contrapositive? Well, if the statement is true, the contrapositive must also be true. Has to, because it's logically equivalent. Alright, if the conditional statement is true, could the contrapositive be false? No, they are logically equivalent. If the conditional statement is false, could the contrapositive be true? No, they are logically equivalent. Alright, so summarizing our information, we know that the conditional statement, if P, then Q, has three related statements. The converse, which is Q implies P. The inverse, not P implies not Q. Oops, that is a P. And then the contrapositive, not Q implies not P. So which, if any of these, are logically equivalent? That is the contrapositive. So I know I'm asking you a whole bunch of different ways, okay, but remember that it could be asked any number of ways on a test or a quiz, and you need to be prepared to answer any one of these. Alright, so now let's talk about the biconditional statement. Remember, biconditional statement means if and only if, and the symbolic notation here is P implies Q implies P. So looking at the two arrows, you see that it could go forwards or backwards. Basically what that means is you're combining your conditional statement with your converse, because remember, converse was Q implies P and the conditional was P implies Q. So we're combining both of those. Notice that we're using both the conditional and the converse to write the biconditional statement. In order for a biconditional statement to be true, both the conditional and the converse have to be true. Alright, so looking at this conditional statement, it says if an animal is a leopard, then it has spots. Okay, that's true. But the converse says if an animal has spots, then it's a leopard. Okay, well, you can think of all kinds of things, a Dalmatian, a giraffe. You only need to provide one counterexample. Because the converse is false, the biconditional is automatically false. In order for the biconditional to be true, both the conditional and the converse have to be true. Alright, so we're going to write three different biconditional statements and explain how we know that they are true. So first off, let's do something that's maybe not math related. Okay, so if you are alive, then you breathe. Well, that's a true statement, right? Okay, that's going to be our conditional statement. Then, let's do the converse. If you breathe, then you are alive. So that's our converse. So now what we're going to do is we're going to combine these two and write a biconditional statement. You are alive if and only if, so it's an if with an extra F, you breathe. Notice that I do not have if and I do not have then in my statement. Why? Because this is a biconditional. So the question is the conditional true? Well, yeah, if you're alive, then you're breathing, right? And then there's the converse true. Yes, if you're breathing, then you're alive. Okay, so then the biconditional statement, if you are alive, if and only if you breathe, has to be true because the conditional and the converse is true. Alright, let's do one more, and then you are going to provide the third example for me, okay? And then we'll discuss your third example in class. So let's do a math one. If a polygon has 3 sides, it is a triangle. Okay, well that's a true conditional statement, so let's write the converse. If a polygon is a triangle, then it has 3 sides. Okay, so that's my converse, and that is also true. So the biconditional statement has to be true, so we write a polygon, oops, forgot my Y. Polygon has 3 sides if and only if it is a triangle. Alright, so my conditional, my converse, whoops, and the biconditional. These are all true because the converse and the conditional are also true. Alright, so what you need to do is you actually need to provide a third example and be prepared to share it with the class tomorrow. Okay? And tomorrow we will begin deductive reasoning finally.